A McFoster-Wheeler UOP offers its coil-type visbreaking process. Their coil-type visbreaker has been claimed to have the following advantages: reduced high-sulfur fuel oil output, a reduction in distillate cutter stock requirements, which makes the distillate available for sale as more valuable transportation fuels, a low cost to upgrade, and a simpler maintenance and decoking compared to soaker visbreaker designs. These coil-type visbreakers can be integrated with vacuum units to eliminate redundant equipment and reduce installation costs. This type of integration was evaluated for a Russian refinery designed to operate a new vacuum unit along with a visbreaking unit. This process diagram shows a McFoster-Wheeler UOP's coil-type visbreaking process. Key features include: 2-zone horizontal type fired heater with soaking coil, high furnace outlet temperatures, short reaction times, quenching of heater effluent with gas oil, fractionator bottoms, or a combination of both, proprietary heater valves and piping arrangements for longer run lengths, and optional integration with vacuum units for reduction of installation costs. A McFoster-Wheeler UOP also offers visbreaker with vacuum flash. In this option, the visbreaking unit is configured in the same way as the basic coil visbreaker, except that the bottom stream from the fractionator is sent to a vacuum tower. The liquid that exits from the bottom of this tower is steam stripped, while the vapor overhead is partially condensed into distillate products that can be processed to transportation fuels. Heavy vacuum gas oil and light vacuum gas oil side streams are removed from the column and combined. Part of the combined vacuum gas oil product is used for fuel oil viscosity reduction, while the remaining portion is utilized as cracker feedstock. This process diagram depicts a McFoster-Wheeler UOP's visbreaker with vacuum flash. A McFoster-Wheeler UOP's two-stage visbreaker is similar to the visbreaker with vacuum flash, except that the combined gas oil stream is sent to a thermal cracker before being routed back to the fractionator. The company claims that benefits of the two-stage visbreaker are that the yield pour point of fuel oil are reduced and light distillates yield is increased. The yield of heavy gas oil distillates may be enhanced by sending the tower stream to the vacuum tower. This process diagram depicts a McFoster-Wheeler UOP's two-stage visbreaker. Another innovation available to adjust the configuration of a McFoster-Wheeler UOP's visbreaker offerings is Wood's technology. According to a McFoster-Wheeler, Wood's process offers several benefits, including a 10 to 15% reduction in fuel oil output, the ability to reduce the fuel oil viscosity and increase fuel oil stability by blending light and or heavy cycle oil into the visbreaking residue, and the production of higher quality high vacuum gas oil feed for FCCUs and hydrocrackers compared to visbreaking with a vacuum flasher. Axon's proprietary visbreaking technology is called Terval. In general, this process increases the residue value by reducing the viscosity of the heavy feedstock by mild cracking. Terval maximizes gasoline and middle distillate products when applied to atmospheric residue feedstocks, with consideration for the residual fuel oil specifications for viscosity and stability. When the feedstock is a vacuum residue, the process is applied to drastically reduce the viscosity to produce commercial fuel oils, with the addition of a light diluent, if needed. Axons offers three variations of its Terval process: Terval T, Terval H hydro visbreaking process, and Terval C. Here is a process diagram of Axon's Terval T process. It is said to achieve vacuum resid conversions of around 38%. This diagram shows the process configurations of Terval H and Terval C. The Terval H hydro visbreaking process increases conversion by about 10% over Terval T and achieves a greater reduction in product viscosity. Terval C, which is configured in the same way as Terval H, uses 50 parts per million of an ultra-dispersed molybdenum additive to increase hydrogen efficiency and produce a stable product. Other benefits include a 40+% conversion and a further drop in resid viscosity. According to KBR, their visbreaking technology boosts distillate production while reducing heavy fuel oil output by 25%. KBR also offers a soaker visbreaking process, which uses longer residence times and lower reaction temperatures. Although the soaker process prevents heavy gas oil product from being recovered, it beneficially lowers the heater fuel requirements. In addition, the company has developed techniques for recycle cracking of visbroken gas oil and special design methods to determine furnace and quench parameters such as cracking severity and soaking coil volume. This diagram depicts KBR's visbreaking process. ABB Lummus Global licenses Shell Thermal Conversion Technologies, which includes Shell Soaker Visbreaking Technology, Shell Deep Thermal Conversion, Shell Thermal Gas Oil Process, and Shell Deep Thermal Gas Oil Process. Additionally, Shell Vacuum Flash technology can be added to visbreakers for additional benefits. The goals of the Shell Soaker Visbreaking technology process are to reduce the heavy oil product by lowering the viscosity of the resid and to maximize production of distillates. The company claims the technology has the following benefits: high tolerance to feedstock changes and operating upsets, enhanced process control, extended heater run lengths, faster turnarounds, and lower power requirements due to the low pressure drop in the heater and generally mild operating conditions. This process diagram depicts the Shell Soaker Visbreaking technology. In the Shell Deep Thermal Conversion process, the bottom stream from a vacuum flasher can be obtained and used as gasifier feed. There are a number of additional benefits according to the company. The process does not require a coke handling system. Also, Shell Deep Thermal Conversion process utilizes the hydrogen in the feed to produce higher quality distillates than the products obtained from delayed coking. Finally, the distillate yield from this process, which ranges from 45 to 68%, is higher than that from traditional soaker visbreaking due to the conversion achieved and the use of the vacuum flasher. This diagram depicts the Shell Deep Thermal Conversion process. Shell offers both the thermal gas oil process and deep thermal gas oil process. In Shell's thermal gas oil process, the company's patented soaker visbreaking, vacuum flashing, and thermal cracking are utilized to yield distillates. Also, the cracked residue stream that exits the bottom of the vacuum flasher is commonly used to produce commercial fuel oil. The Shell Deep Thermal Gas Oil process uses more severe operating conditions to produce liquid coke. This process is said to have conversion levels of 50 to 60%. This process diagram depicts the Shell Deep Thermal Gas Oil process.